If you assume wood frame houses collapse easily because timber seems fragile compared to heavy concrete, structural physics will quickly prove your assumptions completely wrong. While concrete is rigid and heavy, rigidity becomes a major design flaw during a severe storm. In these high wind events, structural elasticity is your ultimate shield. Meet the Wilsons in Tampa, Florida. Their wood frame home is positioned directly in the projected path of an approaching Category 4 hurricane. If their house fails under these extreme forces, they risk losing everything they own. Fortunately, structural physics has a clear plan to keep this timber standing. To understand exactly how this works, we must analyze the microscopic, engineered cellular design that resides within a simple, standard pine stud. Wood is classified as an anisotropic material, meaning its load-bearing strength depends entirely on the direction of the force applied to its structure. Along its natural grain, wood behaves like a dense bundle of high-tensile steel cables, whereas across the grain, its structural resistance is significantly weaker. This parallel cellular alignment gives wood an extraordinary strength-to-weight ratio, allowing it to easily outperform heavy structural steel in specific applications. Mark Wilson understands this mechanical principle well. He carefully inspects his garage walls, checking each vertical pine stud to ensure proper grain alignment. Every vertical pine stud in the wall acts as a critical column, safely carrying thousands of pounds of roof load down through the framing. Young's modulus of elasticity measures this physical property, determining how wood can bend, absorb intense storm energy, and safely snap back into shape. Brittle concrete simply cannot perform this way. Once concrete reaches its strict tensile limit under load, it shatters violently without any warning. Laura Wilson cross-references the house plans, diligently verifying the official lumber grade stamps stamped onto the exposed studs of the walls. These stamps guarantee that each piece of wood meets the precise density and strength standards required for high-risk Florida coastal construction. In the Tampa region, the destructive wind speeds of Category 4 hurricanes can easily tear weaker, non-compliant building materials completely apart. However, modern wood-framed homes possess a hidden structural weapon. Thousands of tiny ductile connections distributed throughout the entire building. Every single nail acts as an individual energy damper, bending slightly under load to absorb the intense kinetic energy of the howling wind. If a structural connection is designed to be too rigid, the storm will concentrate stress at that point until the material snaps catastrophically. Young Tyler Wilson watches his father test the natural elasticity of different wood samples on the workbench in their home workshop. Through these tests, Tyler learns that wood remains dynamic even after drying, reacting actively to the changing environmental forces around it. However, moisture remains the greatest enemy of wood, drastically reducing its Young's modulus and inviting fungal decay that destroys structural integrity. This structural threat is why the Wilsons regularly inspect their crawl space, searching for any signs of water intrusion or dampness. Keeping the timber dry ensures it retains its full elastic potential, leaving it prepared to withstand the maximum design wind loads of the home. A single, weak or decaying joist can compromise the structural response of the entire home when a powerful hurricane strikes the neighborhood. Every single framing element must work in harmony, because if one critical connection fails, the entire house structure can collapse. This engineering concept is known as the continuous load path, and it represents the golden rule of modern structural safety. To protect a building, forces must flow seamlessly from the roof trusses, down through the walls and directly into the concrete foundation. Without this continuous path, the roof acts like a giant sail, generating lift that can rip the house off its foundation. Mark Wilson checks the heavy-duty galvanized metal straps that connect the roof rafters securely to the vertical wall studs. These specialized hurricane ties ensure that the upward wind lift forces are immediately transferred down into the main vertical framing. However, vertical wall studs alone cannot resist sideways forces, and the storm wind will try to rack the house laterally. Lateral racking is one of the primary causes of complete structural collapse during high-speed coastal hurricane events. To prevent this lateral racking, structural engineers utilize OSB shear walls to construct a rigid, continuous structural diaphragm. Oriented strand board, commonly known as OSB, is a highly engineered wood product made of compressed, resin-coated wood strands. The strands are cross-oriented in multiple layers, providing uniform structural strength and stability in every direction across the panel. Laura Wilson carefully inspects the nailing pattern of the OSB sheathing panels installed on the exterior of the walls of the home. Building codes strictly require nails to be spaced exactly 6 inches apart along panel edges to prevent structural shear failure. If a builder cuts corners and spaces the nails 12 inches apart, the OSB panel will easily tear away under pressure. A properly fastened shear wall acts like a deep vertical beam, transferring lateral wind shear forces safely down to the foundation. Without correct nail spacing, the OSB panels will buckle outwards, leaving the vertical studs to face the wind forces entirely alone. Tyler Wilson helps his mother mark the precise nailing guidelines across the surface of a new OSB panel. Tyler learns that engineering precision is not about neatness, but about ensuring the house remains standing during a storm. Modern building codes strictly enforce these shear wall designs in all high-risk hurricane zones along the coastal regions. However, standard building codes only represent a minimum legal standard, which is essentially a D- grade in structural engineering. To guarantee survival during a Category 4 hurricane, you must build your home well beyond the minimum code requirements. Mark Wilson installs structural wood screws instead of standard framing nails at all critical load-bearing joints in the house. These structural screws possess 10 times the withdrawal capacity of nails, resisting the massive pulling forces generated by the storm. If the roof connections hold but the shear walls rack sideways, the entire house will still collapse into ruins. This is why the OSB shear walls must be bound tightly to the concrete foundation using heavy-duty anchor bolts. This continuous metal-to-wood connection ensures the entire timber skeleton behaves as a single, highly elastic, wind-resistant structure. When severe hurricane winds strike a house, they do not just push against the walls, they pull at the roof. Bernoulli equation explains this phenomenon, demonstrating how fast-moving air passing over the roof slope creates a pocket of low pressure. The higher atmospheric pressure trapped inside the house tries to push the roof upwards, creating massive uplift forces. This wind-induced uplift force can easily exceed 10,000 pounds of pull on a standard residential roof structure. Mark Wilson inspects the heavy-duty anchor bolts that secure the bottom sill plate to the solid concrete foundation slab. These foundation bolts must be positioned within 12 inches of every plate joint to prevent the wood from splitting. If these critical anchor bolts are missing or improperly installed, the storm winds can slide the entire house off its concrete slab. Laura Wilson reviews the anchor bolt installation records with Tyler at the kitchen table to verify compliance. Tyler runs his fingers over the thick, heavy threads of the galvanized steel anchor bolt they kept from construction. This solid steel rod represents the final link in the system, anchoring the elastic timber frame directly into the earth. But how does the roof connect to this path? Meet the specialized Simpson strong tie hurricane connector. This engineered steel bracket anchors the rafter directly to the wall stud, completely bypassing the weakness of traditional toe nailing. Toe nailing involves driving nails at an angle through the wood, a method that is cheap, fast, and highly unreliable. Under intense uplift tension, toe-nail joints pull out easily, allowing the wind to rip the roof off the walls. Mark Wilson inspects the attic space, confirming that every single roof truss has a certified hurricane strap installed. He carefully counts the nails in each strap, verifying that 6 nails are present to meet maximum design load specifications. If even a single rafter lacks this metal strap, The uplift force of the storm will concentrate on that specific weak point. Once the building envelope is breached, the entering hurricane winds will inflate the house like a high-pressure balloon. This internal pressure combines with the external wind-up lift, doubling the destructive forces trying to tear the roof away. This double pressure is why window protection is just as critical as roof straps for surviving a major hurricane. Laura Wilson tests the impact-resistant windows, verifying the official laser-etched hurricane certification marks in the corner of the glass. These specialized windows utilize a tough middle layer of polyvinyl butyryl to absorb and dissipate massive physical impacts. A flying piece of storm debris will shatter the outer glass, but the flexible plastic layer remains completely unbroken. If a window breaks and the wind enters, the entire structural load path is put under extreme, immediate tension. Are you risking $100,000 in hidden structural damage? Subscribe to Built Into America to protect your home inspections. Let us examine the geometry of the roof, which serves as the first line of defense of your home against winds. A traditional gable roof has flat, vertical ends that act like a giant wall, blocking the oncoming wind. The wind pushes hard against this flat vertical face, generating massive lateral loads that try to tip the house over. Conversely, a hip roof slopes upward from all four sides, creating a highly aerodynamic shape that deflects wind. This aerodynamic shape reduces wind drag by up to 50% compared to a traditional flat-ended gable roof design. Mark Wilson chose a hip roof design for his home, specifying a slope angle of exactly 30 degrees. Physics proves that a 30-degree slope perfectly balances wind deflection and uplift resistance under extreme storm conditions. If the roof slope is too flat, uplift forces increase. If it is too steep, lateral drag forces dominate. Tyler Wilson watches the wind flow over their small model house in a simple backyard test setup. Tyler notices that the wind slips over the sloped hip roof easily, like water flowing over a smooth stone. However, hip roofs require complex carpentry, utilizing diagonal hip rafters that meet precisely at the central ridge plate. Every diagonal hip rafter must be anchored to the wall plate using heavy-duty steel connector straps. This advanced geometry ensures that wind striking any face of the roof is resisted by all four exterior walls. Gable roofs often fail during hurricanes because their flat-end walls lack sufficient lateral structural support. Without diagonal bracing in the attic, the flat gable wall will fold inward under intense wind pressure. Mark Wilson retrofitted their garage gable wall, installing strong diagonal wood braces to reinforce the vertical framing. These diagonal braces safely transfer lateral wind forces down into the strong horizontal ceiling diaphragm below. The wind resistance of a roof is only as strong as its sheathing, meaning plywood panels must cover the rafters tightly. Plywood sheathing sheets act as a rigid diaphragm, preventing the individual rafters from twisting or buckling under load. If the plywood sheathing peels off, the underlying rafters lose their lateral support and will buckle almost instantly. Laura Wilson double-checks the sheathing nail schedule, detailed on the certified home inspection records. Building codes require the use of ring-shank nails, which feature raised ridges that grip the wood fibers tightly. These specialized ring-shank nails offer twice the withdrawal resistance of standard, smooth-shank framing nails. Using cheap, smooth-shank nails on roof sheathing is a recipe for catastrophic wind damage during a storm. Every single fastener choice matters, because the physics of resistance does not forgive cheap or substandard materials. The Florida Building Code was forged in the widespread devastation left behind by Hurricane Andrew in 1992. Andrew exposed the severe danger of poor connections, low-grade fasteners, and the complete lack of continuous load paths. Consequently, staples were banned, and the building code now mandates strict engineering calculations for every structural joint. Mark Wilson reviews these engineering calculations, confirming that the construction of his home exceeds the current state requirements. Tyler points to a line in the document showing the local wind speed design requirements for Tampa. Mark explains that while the local code requires a 140-mile-per-hour rating, their home is designed for 160. Designing for 160 miles per hour requires all structural components to undergo specialized, rigorous laboratory testing. The standard missile impact test fires a 9-pound wooden 2x4 stud at 34 miles per hour. The wooden missile strikes the test wall section, which is clad in standard OSB and wood siding. The missile strikes the wall head-on, cracking the outer siding but failing to penetrate the underlying OSB sheathing. The engineered wall bends slightly to absorb the massive kinetic energy, preventing the missile from penetrating the interior. If the wall were constructed of rigid, unreinforced concrete blocks, the impact would cause it to shatter instantly. This natural elasticity is why engineered wood is often preferred for impact resistance in hurricane-prone regions. Laura Wilson inspects the window frames, ensuring the high-grade silicone sealant prevents any pressurized air leaks. Under extreme storm pressure, even small air leaks can compromise the internal pressure envelope of the house. Maintaining a sealed building envelope is the difference between minor roof repairs and a total structural loss. The Wilson family gathers in their living room as the first heavy rain bands begin to strike Tampa. They sit together in the warm, lamplit room, listening to the weather updates on their emergency radio. The radio announcer warns residents of rising coastal storm surges and extreme, destructive hurricane-force winds. Outside, the wind begins to howl loudly, testing the natural elasticity of the timber framework of the home. The house creaks occasionally, which is a reassuring sign that the wood joints are successfully absorbing the energy. Wood creaks because the organic fibers slide slightly against the metal fasteners under extreme load. This micro-slippage is actually a deliberate design feature, safely dissipating storm energy throughout the load path. A laser sensor in the laboratory shows how these nailed connections return to their exact original alignment after load release. If the house were built entirely rigid, this massive energy would manifest as rapid crack propagation through the structure. The front wall transfers the lateral wind pressure sideways into the adjacent OSB shear walls. The OSB sheathing sheets resist this racking force, preventing the vertical framing studs from twisting or buckling. The nails holding the OSB panels bend slightly, acting as thousands of microscopic shock absorbers within the wall. This high ductility allows the engineered timber framework to survive repeated cycles of extreme wind loading. Laura Wilson holds Tyler close, feeling a deep sense of relief as the intensity of the storm finally begins to subside. The eye of the hurricane has passed, the wind speeds drop rapidly, and Tampa falls into a quiet silence. Mark Wilson opens the front door, stepping out into the calm morning air to inspect the storm damage. The wood frame home stands completely intact, showing absolutely no signs of structural failure or displacement. Down the street, however, a house built with a poorly braced gable roof has collapsed entirely. That homeowner cut corners on attic bracing and cheap fasteners, losing their entire life investment in minutes. They relied on bare minimum code compliance, and the hurricane revealed the uncompromising truth of physics. But when engineered correctly, wood remains one of the safest, most resilient building materials on Earth. Its organic cellular matrix, which evolved over millions of years to resist wind in trees, works for us. Just as a tree bends in a storm to survive, we can mimic nature to build houses that endure.
Mark, Laura, and Tyler stand together on their front porch, looking out at their safe and secure home. Their house did not collapse because they chose structural elasticity over rigid, brittle construction methods. They built a true continuous load path, locking the roof to the foundation with heavy steel connectors. They utilized OSB shear walls to resist lateral racking and incorporated aerodynamic hip roof geometry. These intelligent engineering decisions saved their home,
proving that physics is the ultimate building inspector. Next time you look at a modern wood frame house, remember the physics keeping it standing. Does your local building code mandate hurricane straps, or are you relying on outdated toe-nailing methods? Have you checked the crawl space anchor bolts in your own house recently? Tell us in the comments below. How does your home design handle wind shear? We want to hear from engineers and homeowners alike. Your comments help build a safer community of construction and physics enthusiasts worldwide. Stay safe, build strong, and never ignore the forces of nature. We will see you in the next investigation.